Okay, let's work on a thermodynamics problem. This is a Rankine cycle. This is for the course ENGR 251 at Concordia University. Consider a 210 megawatt steam power plant that operates on a simple Rankine cycle. Steam enters the turbine at 10 megapascal and 500 degrees Celsius and is cooled in a condenser at a pressure of 10 kilopascal. So pay attention that we are given a Rankine cycle. What does that mean? That means we're going to rely on property tables. And we cannot use ideal gas law because in a Rankine cycle, we do not have ideal gas. We have liquid water, which will be boiled into steam, and steam is going to push on the turbine to generate work. So again, Rankine cycle means liquid water, steam, superheated steam. Forget about ideal gas law. Before we start the question, let's draw the diagram of this cycle. I personally always start from the pump. And then it goes to boiler. Which boils the water and convert it into superheated steam. After the boiler, we have what does the work, which is turbine. And finally, we have condenser, which condenses superheated vapor back into liquid water. It rejects heat. I'm also going to label what happens at each component. At boiler, we have heat in. Heat is added here. Condenser rejects heat, so heat out. Turbine does work out. And pump requires work, so that's work in. Also, we have two isobaric and two isentropic processes here. The boiler, this is isobaric. Same as the condenser. And for the pump and turbine, they got isentropic. I'm gonna put a side note here. What do those thermodynamic terms mean? Isobaric means in this process, pressure is not changed, so pressure is constant. Isentropic means in this process, entropy is constant. And for this process to be isentropic, you need to meet two conditions. First, adiabatic, meaning heat is constant. No heat is added, no heat is coming out. And the process must also be reversible. These two combined, that gives you isentropic process. Okay, let's also label states. So this is state 1, state 2. Now let's put the values we are given. First of all, we have the power output, and that is the net workout megawatts. Same as 210,000 kilowatts. Pay attention that I'm putting net because this is work net, not just the power given by the turbine. It's also a big W because we are not dividing this value by per unit mass. You don't see per kilograms. So this is big W. And we are putting a dot because it's watt. Watt is joules per second. So this is power. So this whole value, 210 megawatt, this is big W dot, and it's work net. Now we can start solving problem. State 1. By the way, we're going to need at least 2 independent properties for each state to unlock the whole problem. So state 1, okay, let's also label the pressure and temperature we are given from the question. It says steam enters the turbine at 10 megapascal and 500 degrees. So enters the turbine, that means state 3, P3 is equal to 10 megapascal, T3 is 500 degrees. Since state 2 to state 3 is isobaric, so P2 is also 10 megapascal. And is cooled in a condenser at pressure of 10 kilopascal. Condenser, that's pressure 4, 10 kilopascal. Since state 1 and state 4, they are isobaric, pressure 1 is going to be 10 kilopascal. Okay, so, and again, to solve this Rankine cycle, we're going to rely on property tables. So, state 1, we have pressure. What else do we have? Nothing. So we're going to find some information from the property tables. In the pressure table, we see that T1 is equal to Tsat is equal to 45.81 degrees Celsius. We can also write down the value for specific volume. Pay attention, this is VF, not VG, because at state 1, it's liquid water, there's no steam, it's 100% liquid. We can also put H1, which is equal to HF. Now we can calculate the work input, which is the pump work. Here we're going to apply the first law of thermodynamics for an open system, because for a pump, for any component here, it's open system. Mass is passing through this component. I'm gonna write down the full version of this this equation, and then we're gonna cancel out a lot of terms. So this is what a full term looks like. This is kinetic energy. This is enthalpy. And this is potential energy, PE. No velocity, no altitude, they are 0. So, and since we don't have mass at this point, so everything must be divided by m. So it's small q minus small w, and it ends up with enthalpy change. Delta Q is 0 because it's isentropic process, and isentropic means adiabatic, so heat is 0. So we are left with work 1, 2, swap is that. And what is work? Work is actually the pump work, right? So we're going to use V1 times the difference in pressure. And since this work should be a negative value because it's work in, so pressure is small pressure minus big pressure. In the end, that will give us a negative value. 10 kilopascal, everything is in kilopascal. Kilogram, kilowatts, kilo. That gives me negative 9.99. Once I have work, I can use work to get H2. H2 will be H1 minus 1, 2. H1, we have H1 from the property table. And pay attention, work is negative. So minus minus. Why is H2 bigger than H1? It's because, well, pump gives a bit of energy to the liquid water. So that's why H2 is greater than H1. And then we can move on to state 2. There isn't much we're going to need for state 2. We have pressure 2, and we have H2. Like I said, I need at least 2 independent properties for each state. Well, we have 2, so state 2 is done. Let's go to state 3. State 3 is from the boiler to turbine. We have pressure, we have temperature, given from the question. And these two are independent properties. So state 3 is done. Is it? It is not done for state 3. We're going to need 2 more values for state 4 from state 3. We're going to need H3 and S3. Enthalpy and entropy as state 3. So again, using, well, in this case, we're going to use superheated table because look at this pressure. That's a huge pressure, and this is a huge temperature. And after the after the boiler, it's 100% steam, and the steam means superheated steam. So I'm gonna copy some values from the superheated table at this pressure and this temperature. So H3 and S3 Why do we need H? It's because we need H3 to calculate work for state 4. And why do we need S3? I'm not going to answer this question right now, but you will see. Since we have information as state 3 and state 2, and boiler is being sandwiched between these two states, so we can calculate the value for heat in. Heat in, let's call it heat 2-3. And the boiler doesn't do any work, which is pretty obvious. So work is 0. So Q23, which is work in, heat in, is just the difference between H3 and H2. Minus H2. So Q in is this. Now we can go to state 4. State 4 is our turbine, which creates work. We have P4, that's 10 kilopascal. What else do we have? Well, nothing. We don't have temperature. We don't have enthalpy. We can't find enthalpy with just one temperature, with one pressure value. But look at this, state 3 to state 4. We got isentropic process. And in state 3, I have already written down S3. So I can just copy that value for S4 because S3 is the same as S4. They are isentropic process. Same value. And this is the trick. I'm going to use entropy to get my enthalpy. And then I'm going to use enthalpy to get my work. Now, let's go to the property table at 10 kilopascal. We see that at P4 is equal to 10 kilopascal. What we have? We have SF at this pressure. That's around this. And SG. Do you see anything here? Our S4, it's 6 point something, and that's in the middle of SF and SG. What does that value tell you? That basically says that at state 4, we have a mixture. Why? Because, well, the lower end and higher end, well, our S value is between our lower end and high end. So that's a value. That value tells us we are in a mixture state. Since we're in mixture, next step obviously to find quality. I'm gonna write this down. Since S4 is between SF and SG at the given pressure, as state 4 is a mixture with quality equal to S4 minus SF divided by SFG. Plug in values, we got this is our X value, which is around 80%, pretty high. That's normal. And we can use this X value to get our H4. H4, we're going to use HF plus X HFG. HF and HFG, well, we can find them easily at pressure from the pressure table at 10 kilopascal. Plug in numbers, we got that gives us this much for H4. Since we have H4, we also have H3. We can calculate the work output at the pump, at the turbine, sorry. Let's call it work 3/4. Again, using the first law of thermodynamics for open system, very, very simplified version, that is this. Does the pump do work? 100%. Does the work, does the pump, what I'm keeping saying pump. Does the turbine does work? That's his job. Does he do anything to the heat? No. So heat is gone. We end up with the difference between enthalpy at state 3 and state 4. Once we have turbine work, we can calculate our net work. Net work is just turbine work minus pump work. Still, this is small letter w. Work 3, 4, this is our turbine work minus work 1, 2, that's our pump work. However, here, I'm not doing minus minus. I'm doing minus absolute value. Otherwise, my work net is going to be greater, which is impossible. And that gives me this much work output. Since we are given the big W net, and now we have small W net, we can calculate the mass dot. Again, everything is in kilojoules, kilowatts. There's no mega in this course. Let's put some values. Kilowatt per kilogram. Oh, this is kilojoules per kilogram. So we have, let's do a unit check. Kilowatts, it's kilojoule per second divided by kilojoule per kilogram. So we end up with kilogram per second, which is the unit for mass dot. And the value is 164.8 kilogram per second. Now we can calculate our system's thermal efficiency. Thermal efficiency is a very simple equation. It's basically what you get from the system divided by what you give to the system. What we get is work net. What we give is heat in. Heat in is heat Q23 calculated at the boiler. And work net, we just get it out. And that gives me around 40% of efficiency. Let's double check with Carnot. Because Carnot says the maximum idealized efficiency. T low divided by T high. It's in Kelvin here. Pay attention. And T low, where is T low? T low is at pump. It's the lowest temperature, 45.81 degrees Celsius. And highest temperature happens at boiler, 500 degrees. That gives me this much efficiency. We see that the actual efficiency is less than Carnot, which makes sense. And now we're gonna need to draw the diagram, the TS diagram, which is a bit hard. First of all, we have two pressure lines. A high pressure happening at P2 and P3, and the low pressure happening at P1 and P4. So we can draw these two pressure lines first. This is my low pressure line, and this is my high pressure line. And we can draw the dome. Not pretty. And yeah, let's say this is the low pressure, so P1 and P4, that's 10 kilopascal. And this is the high pressure, and that's 10 megapascal. Let me change color. So the actual path for this cycle is coming from this dot, going up, straight up. This is not even straight. Do better. Okay, starts here. This is 1. And this is 2. And once it reaches 2, it goes here, follows the same temperature line. And since we know that at state 3, we are in superheated vapor, so we're going to come a little bit outside, because we're in superheated zone. If you're inside the dome, that means you're mixture. If you're right at this dot, that's saturated vapor, but we are not there. We are beyond that point, so we need to come out a little bit more. And then from state 3 to state 4, well, theoretically it's a straight line downward, but like I said, I'm not great at drawing, so I'm gonna tweak a little bit. I'm gonna do this, but in theory, from state 3 to state 4, it's a straight line down. And 4 to 1, this is 4. Why 3 to 4 is a straight line is because delta S doesn't change at that point. So S3 is equal to S4. And here S1 is equal to S2. But the thing is, I'm not great at drawing. So let's put a side note here. If this is an exam, say state 3 to state 4 should be straight down. Because it's a isentropic process. And why is state 4 inside our it's on this flat state, flat part, is because in state 4 we have a mixture, right? We calculate, we have a value for mixture. So state 4 right here, and let's call this point X is equal to the value we had before. So in theory, the process looks like this. Looks like this. This is our 3. This is our 4. This is 1. This is 2. And the dome looks like that. And this is a straight downward line. Same as from 1 to 2, it's a straight line. And that's it for this Rankine cycle problem.